Okay, so I want to talk just a little bit about friction here. And it's going to write friction. So we learned in a previous class that friction is basically what it is, you know, microscopically, two surfaces have imperfections in them. And as you attempt to slide one surface across the next, the fact that the object is pulled down by the force of gravity, so it has weight equal to mg, right? You know, basically forces these objects together or pulls them together. Now, microscopically, there's going to be little pits and grooves and so on, and as you slide one across the other, there's going to be a resistance. What is the nature of that resistance? What is it really that resistance is made of? What is causing it? Right, electrostatic repulsion, right? You can't generally force two surfaces into each other because the electrons, or the negative charges on the outer shells of electrons, repel. So this is kind of the basic nature of friction as we understand it, okay? So if I look at a box on a surface and start to draw the forces, I have weight equal to mg, pushing down, and since how there's no acceleration in the vertical plane, I must have an upward force. We say that that is the normal force, and that's equal to just the opposite of mg. Okay. So as it stands, if there's nothing else going on, that's sort of the end of the story. But if we attempt to apply a pushing force to this, let's call it Fp, we will find that there will be resistance. Okay, there's a reactive force. We call this friction, that reacts to the forward pushing force. So we can increase the forward pushing force up to a point. At the point when the friction can no longer be equal to the pushing force, this object will start to accelerate. So it's reactive to a point, and then beyond that point, it still exists, but it's going to be lower than the pushing force, and will have an acceleration. Okay. Once we get something moving, if the pushing force and the frictional force are equal, again, the object will just continue to move at a constant rate. Okay. So, what sorts of things do you think would dictate the amount of frictional force, that we're going to find in this scenario? What sorts of factors would play into how much friction there will be? Okay, good. The weight is important. I think it's pretty obvious that if you're sliding like one book across the tabletop, you can sense that there's some frictional resistance. But if you put like 10 or 15 or 20, eventually you're going to get so much friction that you're probably going to have trouble making the pile of books slide, right? So weight definitely plays a role. And that should make sense. As weight increases, these are forced into closer and closer contact. And it takes, I guess, more effort if you want to perform the slight lifts and so on that is required to make this slide across the other surface, right? They're just crammed closer together. You can mimic this with your hands and fingers if you put them together. You squeeze hard and try to slide. It's much easier if you just lightly hold them together, right? It's a similar concept, just at a microscopic scale. So that's one thing. What else? What else comes into play? What's that? What they're made up of, absolutely. So this is the type of object. If this is polished steel and this is a glass surface, you might find some fairly low friction. If this, is a cube of rubber and this is asphalt shingles, you're going to find that there's going to be a lot of resistance, right? If this is ice and this is Teflon, it's going to be easy to slide. If it's, rusty metal and sandpaper, it's going to be hard to slide, and so on, right? So weight is one thing, and technically it's not the weight really, it's the normal force, because think about it, if we were to remove this surface, there would be no friction. Weight wouldn't change, but but there would be no normal force, right? So it's actually the normal force that's important here. If we remove the surface, we effectively remove the friction. So it's got to be the actual upward force that is really, giving us the friction at the end of the day. And then the type of object. So this is where the concept of frictional coefficient comes in. Okay, And what that is it's a number, it's a value that we assign to indicate, the given amount of friction that we're going to have based on what the surfaces are made out of. So we have a little formula that helps us deal with this, that ties these two things together. So what we say is force of friction is going to be equal to mu times the normal force. Maybe a better way to think about it is, it's a mu, yeah, like the Greek letter mu. It's not a U, it's a mu. I wonder if I could probably actually find a proper mu, but whatever. It looks kind of like that. And what I guess it is really is it's the ratio of the frictional force to the normal force. So it ties the two things together. Both of these are measured in newtons, so if you divide them through, newtons would cancel out. So what that means is mu is unitless. Coefficients oftentimes are unitless, right? They're relating they're relating something in the vertical plane, I suppose, to something in the horizontal plane. Those two things are measured in the same units, and so this is the coefficient that ties those two things together. Okay, so this is a sort of an important formula when we're talking about friction. Ff equals mu times whatever the normal force is. All right, so far so good. Now it gets a little more interesting when we put our object onto a slope. Okay, so if we start to analyze what's going to be going on here, well, we realize there's a normal force up like this. In order to make the resultant forces apparent, let's put our weight down. That's equal to mg. Let's write our normal force here, perpendicular to the surface, but we'll move it over here. And our resultant accelerating force is going to be down in this direction. And we have some slope there, some angle, and that angle will also work over here. We went over that in a previous class, how that is the same angle by just geometrical rules. Okay, so Fn, the normal force in this case, is going to be equal to whatever weight is times the cosine, right, of that angle, because it's the adjacent angle. This is the hypotenuse, and the hypotenuse is found as mg. So we could write this as W times the cos of theta. Or better yet, since W is equal to mg and will likely be given a mass, or we might not, we can write it like this. So normal force is equal to mg cos theta. Okay? The accelerating force is, again, based on the weight, so mg, however, now we're the opposite angle, sine theta. Okay? So normal force points up, accelerating force points to the left. On its own, normal force isn't really interesting in this question. I mean, it just, is saying, okay, so we've got this normal force up over here. On its own, doesn't really tell us a whole lot. However, what it can lead us to is what the frictional force is, right? So as an object tends to slide down the plane, there is a counteracting frictional force essentially working against Fa. If the force of friction is large enough, the object will stay stationary. Okay? And remember, it's reactive, so what it'll do is it'll exactly equal to whatever Fa is until Fa gets large enough that the force of friction can no longer counteract it, and the object will start to slide. Can you think of ways or a way anyway, to increase Fa in this scenario? What are some ways to increase the value of Fa? Well, yeah, okay, I guess I could come up here and push it. That's one. Sure, I could push on this. Increasing the angle, absolutely. Okay, so as the angle gets larger, okay, the sine of the angle also gets larger, and so the Fa value gets larger. Okay. Interestingly, as the cosine gets larger, as the angle gets larger, what happens to the cosine of the angle? What's the cosine of 90? Let's say we increase this to 90 degrees. Cosine of 90 is, I'll give you a hint. It starts with Z and ends with 0. Yeah, it's 0. And if you look at the picture, just imagine that, let's say this is a hinge here, and this is movable, okay? So this represents a ramp. This represents the horizontal surface the ramp is on, and this is just like, something that we prop it up. Well, imagine as we increase the ramp towards 90 degrees, okay, what we're doing is we're basically putting a lower and lower and lower value on the normal force until this is horizontal. And once this is completely horizontal, there's no normal force anymore, right? So there's kind of a double action happening. As we increase the slope, we're increasing FA, and we're decreasing the amount of friction. What do you think happens when we get to 90 degrees? What if this becomes F equals mg sine 90? What's the sine of 90? Say it. If the cosine of 90 is 0, the sine of 90 might be... You guys don't take trig? You haven't taken these functions? You do the cosine of 90 in your calculator if you don't know what it is. Or do the sine of 90 in your calculator. Good, it's 1. Perfect. So what we're saying is, when this gets to be 90 degrees, the accelerating force becomes equal to... what? This is 1. If sine of 90 is 1, FA becomes... just becomes equal to weight, right? We increase this, we've decreased normal force to 0, and we've made the accelerating force equal to gravity. So, another way of looking at a ramp, right, is it's kind of like a transition between this object being sitting on the surface. When it's on the surface and theta is 0, right, the accelerating force is 0, right? mg sine 0 is 0. mg cosine 90 is just mg, so normal force is as large as it will be. So it's a transition between full normal force, 0 accelerating force, and full accelerating force, 0 normal force. All right, and there's all these various angles in between. Do you remember what a sine and cosine graph look like from last year? Okay, well, we won't get into that too far, but okay. Okay, so let's solve for a couple of things here. Okay, so first thing, if mu equals 0.02, mass is 4 kg, theta equals 40 degrees, find the acceleration of a block. Okay, so that's what we want to do here. So we'll go through and we'll calculate everything that we can. So what we're going to need here, if we think about it, I'll just roll back up for a second. What we're going to need here is we're going to need to figure out what's the frictional force, what's the accelerating force, and then what's the net force. Okay? So let's go with FA first. Well, that's mg times the sine of theta. So we said the mass was 4 kg. We're going to multiply that by our value of acceleration due to gravity, 9.81 meters per second squared, times the sine of 40 degrees. Make sure your calculator is in degree mode, and let's quickly solve for that. Don't apparently have a working calculator. So what you should get is 25.2 newtons. And that is in the leftward direction, kind of leftward down the slope. Okay, so the force of friction we'll now figure out. It's going to be mg cos theta times mu, right? There's Fn and there's mu. Okay, so force of friction is mu times Fn. So Fn is calculated again, mg cos theta times mu. So we get 4 kilograms, 9.81 meters per second squared, times the cos, 40, times 0.02. Probably not going to be a lot of friction here, but let's calculate that. Okay, so we get 0.6 for the friction in this case, which is pretty small. 0.6 newtons. It is in newtons, yeah. So if we want the net amount of force here, basically we just say, okay, we've got 25.2 to the left, plus something that is in the opposite direction. So we essentially subtract it. And we should get 24 point, we get 6, right? 24.6 newtons left. Okay. Now what we want to do is we want to find acceleration. So acceleration should be, well, if F equals ma, then A should be equal to the net force divided by the mass. So 24.6 newtons divided by the mass, which is 4 kgs, so a little over 6. 6.2 meters per second squared. So something that people often like to say, they like to say that a ramp dilutes gravity. Okay, dilutes gravity. If you could have a frictionless ramp, it would still dilute gravity. Should we try one with a frictionless ramp? What's that? Well, when I say dilute gravity, I just mean that it causes something to accelerate at less than the acceleration due to g. So somewhere between 0 and 9.8. So let's try one more really quickly if we can. Okay, so we'll try one more quick example. Let's just put a ball on a ramp, and we'll say that this ball is nearly frictionless when it's interacting with the ramp. Okay? Don't like that. Just gotta make sure I'm picking the right thing here. Okay, so here's a ball on a ramp. Okay, and we want this ball to roll down the ramp, and let's give it a theta value equal to, I don't know, say 20 degrees. Okay? If this ball is rolling down the slope at 20 degrees, and we say mu is essentially 0. It's not really 0, but it's essentially 0. We'll use our imagination that we have a very, very, slick surface that provides very little to no friction. How would we go about finding the acceleration of this down the plane? That's not a very nice drawing. Is it possible to do this? Note, I've not given you the mass of the ball. If you do it without the mass of the ball, what do you think? Yeah. So we've got weight here, right? That's mg. We've got Fa here, which is mg sine theta. But we don't really care about the normal force because we don't know the mass, and we just said there's no friction, right? So can I solve for the acceleration of an object rolling down this surface without knowing its mass? What do you think? Okay, so let's figure out how we can say that. The net force here, the net force is equal to what on this drawing? What is the total amount of force equal to on this drawing? Is it not equal to that, the accelerating force, right? Isn't that the only force that's going to be playing a role here? We say there's no friction. There's no friction, there's nothing opposing it. It's the only important force, right? We know that there's enough normal force to keep it from accelerating, in this direction, but we're interested in this direction, right? There's no acceleration here anyway, so we know those forces are canceled. So the net force really is simply going to be equal to Fa. So now what we can do is we can say, well, what are those two things equal to if we break them down? This is the mass times the acceleration. This is mg sine theta. And what do you see in both sides of the equation? Acceleration on a slope with no friction works out to just be g sine theta. So pause for a second and let's find it for this. So what we'll get is we'll get 9.81 times sine. I don't know why I put sine in there twice. It's not necessary. Sometimes it'll let me erase with the back, but There, g sine theta, that's better. Okay, so 9.81 times the sine of 20 degrees. Okay. Yeah, exactly. So this is where the concept that you're diluting gravity comes from, right? It's just saying that the acceleration will be less than the acceleration due to gravity, and as this increases, right, we will approach 9.81 as as this goes to 90, it goes to 1, so a just becomes g, right? It'll fall straight down. So can we do the same thing if we now say there is a mu value? What if there is mu? So what if we change this problem? We say mu is now, I don't know, 0.2. Okay, well, watch what happens. Now all we have to say is F net is going to be equal to the acceleration, or the accelerating force, but now we have to take into account the force of friction, don't we? Plus the force of friction. Now these are in opposite directions, so this will be, let's call it positive, and this will be, let's call it negative. Okay. What if we find that just an aside here, what if we just do basic calculations and we figure out from our formulas that the force of friction is actually larger than Fa? What would happen in that scenario? Right, it wouldn't move. It wouldn't move. Friction is reactionary only. In other words, it can't cause movement. So if we calculate that friction is larger than accelerating force, it just sits still. It does not accelerate up. Okay? What a magical world that would be. Okay? So let's work out what all these things are. Okay, so that's ma, right? That's what net force always is. This is mg times the sine of theta. And we're going to add here, now remember, it's in the opposite direction, so we're going to show that with a vector, right? Mu mg cos theta. Okay, now one convention that I'm using here is I'm not using negative values for g. Okay, you could, but then you would just kind of, I guess, invert everything that you're doing here. So I find it easier to just leave g as positive and dictate direction with my negatives. Okay, I don't know if that's like super politically correct physics, but to me, I mean, you're using your own common sense here anyway, right? One is that way, one is that way. The net force is going to be the difference. So what happens here? So how we can deal with this, if you look, is we can pull mass out of here. We can do this. Just pulled mass out of here, right? And then I'm going to divide mass off either side. So what I'll get for acceleration when there is friction is g sine theta minus mu g cos theta. This is like a universal formula that will give you acceleration on a given surface if you know the mu value. Okay? Interestingly, the weight of the object doesn't matter. For a given slope and a given mu value, acceleration will always be the same. Okay? Does that make sense? And if it doesn't feel comfortable, it's kind of the same logic that no matter what the weight of an object is, if I drop it, it accelerates towards the ground at the same rate. Okay? Are we good?